So let's talk about something completely different today. We're not going to talk about any programming, any Python or anything like that. We're going to talk about combinatorial games. So a combinatorial game is generally going to be considered as a two-player game. We can have versions that are one-player games, multiplayer games with more than two players, and we're going to focus on what are called impartial games. And impartial games are where the two players are interchangeable. And so we'll talk about what that means in a couple of minutes. So in a combinatorial game, the players take turns. We call this kind of game a sequential game. So the play proceeds in sequence. There is a winner at the end of a combinatorial game. So games that have draws are not formally part of combinatorial games. They can be analyzed in similar ways. Games that have draws can sometimes be included in the definition. We're going to focus on games that have a clear winner at the end. In a combinatorial game, there's no hidden information. Everything is completely visible. This is called perfect information. Everyone can see everything that has happened. Everyone knows what everyone has available. Everyone knows what has happened in the past. And so the perfect information changes the situation from other games where you don't necessarily know what options the other player has. In a game of perfect information, you know exactly what options they have because you know everything that has happened and everything that's available. In a combinatorial game, both players have the same gameplay options. This relates back to the idea of impartial games. And there's no chance at all involved. There's no dice, there's no dealing cards, for instance, where you don't know what you're going to get or you don't know what the other player got. These games are strictly skills-based. Everything is about how well you can analyze the situation and make the appropriate move in that situation. So some non-examples of combinatorial games. Again, a couple of these are sometimes considered by some people as combinatorial because you weaken a little bit of the conditions or you replace some of those conditions or parts of the definition in other ways. But for example, tic-tac-toe fits most of the requirements, but the impartiality portion, players can only place their own letter, so X and O are different things. And draws are possible at the end, so formally not a combinatorial game. Chess is another example. Players can only move their own pieces, and draws, again, are possible. Poker, not a combinatorial game because it relies on chance. And there's imperfect information. You don't know what the other player has. You might be able to gain some information as play progresses, but you never have complete information about what's going on. Okay, so we're going to analyze a couple of games, and our idea is when we analyze a game and we try to determine a strategy, really what we're doing is developing an algorithm of how to win. We assume that both players know how to play the game and that both players will play perfectly. Now that doesn't happen in real life, but in terms of analyzing the game, we make that assumption. We don't determine our strategy based on the other person not knowing how to play. But the strategy involves what do you do in every situation. So a complete strategy for a combinatorial game would include instructions of what to do exactly in every scenario. If the player does this, if the other player does this other thing or this other thing, whatever, there's always a response for every scenario. So we're going to look at a simple game that we'll call the 64 game. And so we're going to call our players player 1 and player 2 just because the first one that moves and the second one that moves. So player 1 is just going to choose a whole number, a positive integer from 1 to 8 inclusive. And then player 2 is going to add to that number with their own choice of a number from 1 to 8. And then the players are going to take turns adding from 1 to 8 on their turn. They don't have to add the same value as before, but they can if they choose. You can reuse the values as many times as you like. You just keep adding from 1 to 8 on your turn, and it adds to 1 total. So whatever player 1 adds in, player 2 adds to that, player 1 adds to the new total, player 2 adds to that total, and so on. And the goal of the game is to make the total exactly 64 on your turn. So what you need to do is pause the video, find a partner, and play this game and see if you can figure out a strategy. How do you win this game? All right, so hopefully you found someone and you had a chance to play a few games. And maybe you started to see some things that were important, some ways to guarantee a win. If you only got to play a few times, then maybe you only noticed some things that happened toward the end of the game and you thought that maybe the beginning of the game wasn't so important, but at a certain point it started to become important. So we're going to talk about analysis of games in general, and then we'll specify to the 64 game. We're going to think about the current score and whose turn it is to play as a state of the game. This is the current state. And at a certain point, whatever the value is, whatever the total is, that might be advantageous for the person who just played, or it might be advantageous for the person whose turn is next. So a P position is a board state in which the previous player has the advantage. Whichever player leaves it in that state has the advantage at that point. So if you can determine a P position, this would be in this particular game, a number that you want to leave the score at so that your opponent is at a disadvantage. An N position is a position that the next player to move has the advantage. So if you receive the board in a P position, then it's a disadvantage for you because it's your turn to move and the previous player has the advantage. An N position is one that whoever's going to move next has the advantage. So you would hope to receive the board in an N position if it's your turn and leave it in a P position at the end of your turn. The idea of the analysis is that an N position can always be turned into a P position. So the next player has the advantage. The board comes to them. The advantage for them is that they can turn it into a winning state. It can not necessarily win the game yet, but they can turn it into a board that they have control of, or a game that they have control of. And the other side of that is that P positions, previous player advantage, can never be turned into a P position after you make a move. So if you receive the board in a P position, that means the previous player has the advantage. There's nothing you can do to take that advantage away from them. So player 1, let's say, leaves the board in a P position state. Player 2 makes a move, and all it does is prepare the next player. Again, player 1, going back to them, prepares that player for the next good move, the next correct move in the game. So the only way that the P positions switch into a P position would be if someone made a mistake somewhere, right? If player 1 had the advantage and then messed up and gave the advantage away. But you can't do a direct transition from P position to P position. And we'll see that specifically in the 64 game. So in the 64 game, the P positions, obviously at the end of the game, having the score be 64 is a P position because the previous player, the player that made the total 64, wins the game. But to leave 64 at the end of the game, you can see that you want to leave 55 on your previous move before that. If you leave a total of 55, then the other player has to play between 1 and 8, and so all they can do is leave the total anywhere from 56, maximum is 63, and so then on your turn, when it becomes your turn again, you can then make the total 64. So 55 is a P position. The previous player has the advantage. The other player has to make a move. They have to add to the total, and the only thing they can do is add from 1 to 8, and the end position they leave it in will be something between 56 and 63, and so then when it is your turn again, you're the next player, you have the advantage because from that scenario you can go to the win. Well, so we know that 64 is a desired goal, but now 55 becomes a desired goal. And the new question is, how do you guarantee that you can leave it on 55 at the end of your turn? To leave it on 55 at the end of your turn, you need to be able to leave it on 46 on the turn before that. And so the idea is these P positions, we're working backward from the end of the game to figure out where do we want to leave it. We want to leave it at 64. Okay, well, to do that, we need to leave it at 55. Okay, to do that, we need to leave it at 46. And in each case, we can analyze what happens. The other player has received the board in a P position, which means we have the advantage. They receive the board. All they can do is move us closer to another P position, but can't reach the P position. And so we then get the board back in a scenario, a state that we can update to be the position that we want it to be in. And so if we get to 46 and we don't make any mistakes, they can't do anything about it. It does not matter what they do. We have a move that will get us to 55. And then whatever they do, it does not matter. We then have a move that gets us to 64. Now, if we're writing code for this, we do have to figure out what value to add and so on. But the idea is if we know those P positions, once we reach a P position, we can then maintain control of the game the rest of the way. And so the idea is we need to work our way back further. How do we guarantee that we can reach 46? What do we need to be able to do to get to that position? And we keep working our way back further and further until we figure out what our first move should be. Now, it might be in some games that the first player has the advantage. In other games, it might be that it's the second player who has the advantage. And so in a game like this, once we have solved the game, that is, once we know all the P positions and we know who can reach those positions, then it's not really a fun game to play anymore. A game like this, once we know the P positions, the game is very boring. If we both know how to play and we know the P positions, we just have, once we decide who's player 1 and who's player 2, we know who's going to win the game, because we know what player 1's first move will be, and we know that player 2's move will be whatever, and back and forth, back and forth. If it's a player 1 win, just going first guarantees that you're going to win, because you're not going to make a mistake. If it's a player 2 win, well, player 1 does whatever they're going to do, and then player 2 puts us onto a P position. Player 1 doesn't have any control, and player 2 just maintains control of the game all the way through. But most games are more complicated than the 64 game, and we may not know all of the P positions. And so you don't know, was this a good move or not? I don't know. It has some features of a good move. If you think of something like chess, again, chess doesn't quite fit our formal definition of combinatorial game, but it's rather close. You have some ideas that, yes, this was a good move, or sometimes when you make a mistake, you know for sure, oh, that was a very bad move. But overall, we don't know the exact positions of who is really able to guarantee they can win from a particular position of the board. But if anyone did ever figure that out, then people would pretty much, well, in this case, the number of P positions would still be so large, and there would still be the possibilities of making a mistake and so on. But if it were to become a solved game, then it would be a less interesting game, at least, in terms of, do we really have to worry about it? We know, here's the position, you made this move, okay, now I need to put things into this position, and then whatever you do, it would become a, well, again, what is called a solved game, and those are less interesting than ones people don't know how to guarantee a win to. All right, but this collection of P positions helps us build our game strategy. What do we do if we know all of the P positions? We can then specify exactly, I do this to get to this P position, and then you have 8 options, and whichever option you do, I'm going to do this thing for that option, and the other thing, and the other thing, and so on. All right, so we see that the 64 game, once we know the P positions, the N positions aren't really interesting anymore. It's the P positions. How do I want to leave the board at the end of my turn? Now, we often modify games once we have solved the game. We make a slight change to it. So we're going to have the same setup. Player 1 is going to choose a whole number from 1 to 8. Player 2 is going to add from 1 to 8 to that number. They're going to alternate. But this time, the first player to reach 64 or go over loses the game. And so we just made this change of, you want to get to 64 or you don't want to get to 64. And so in games, often the idea is that you want to be the last one to move, but in other games, you don't want to be the last one to move. And these games where you don't want to be the last one to move are called the misere version of the game. Please excuse that very poor French pronunciation. The idea of games is that sometimes you want to make that last move, you've captured the last piece or something. Some games you don't want to do that, but you analyze them in the same way. The goal is P positions are winning positions for you. That's the board that you want to, or the state you want to leave the game in. And so whether it's the last move wins or last move loses, the idea is the same kind of analysis. So again, pause the game and play this misere version of 64 and see what happens. See if you can determine the P positions. All right, so in analyzing 64 misere, the P positions are different than before, right? You want to, this time, leave the board at the end of the game, leave it at 63. How do you guarantee you can leave it at 63? You leave it at 54 on your move before. How do you guarantee 54? You work your way down and you can see the P positions in this game. And so the question you ask yourself is, which player is guaranteed to be able to reach these positions? So the P positions, when you work your way to the end, in the first game, you'll see that one of the players has the advantage, and in this game, the other player has the advantage. And so to describe the appropriate winning strategy then is the same kind of thing. It's based on you reaching a P position, and for each possible move by the other player, you describing exactly what you would do. In this case, we can describe it in English, and the English description is easier than, say, the specific descriptions that you would have to provide in code. Maybe in this particular game, maybe not. You could describe what to do. What value am I going to give? It depends on what the other player has done. That's how much more you're going to add in. But the goal is you keep hitting the P positions, and then you will win the game. Now, something to think about after you've played this is the P positions in the 64 game. The numbers aren't as readily familiar as they are as the P positions in 64 misere. So if you're playing against someone a bunch of times and they don't know how to play yet, and they start seeing that you keep going to the same total, then they may start to recognize a pattern and they may start to figure out what they need to do. And maybe not. But when we're analyzing games, we're not assuming that about the other player, right? We're assuming that both players know how to play the game perfectly. So our analysis isn't really about playing the game against someone at all. It's how we learn to play the game. It's how we learn to analyze the games. But the idea is more about developing an algorithm and then being able to prove that that algorithm is correct. In other words, if this particular player plays in this particular way, they will win the game every time, regardless of what the other player does. All right, so another game that you may have seen before is a game that we're going to call the 3-4-5 game. And so we're going to begin with 3 piles of stones or whatever, some objects that you have, something to hand, 3 different piles, and there's going to be 3 of them in one pile, 4 in the second pile, and 5 in the third pile. And the way this game works is, again, the players are going to alternate turns, and on your turn, you will pick a pile and then take as many of the stones from that pile as you like. And you take them away, you put them off to the side, they're out of play now. So you can pick one pile and take as many as you want from that. You have to take at least one, and you can take all of them if you like. So any number from 1 up to how many ever are there. And then it's the other player's turn. They're going to do the same thing. They're going to pick a pile that they want and take as many as they want from that pile. And you're going to go back and forth. You can pick different piles each time and different numbers from the piles each time. And the goal in this game is to pick up the last stone. You don't have to pick up just one stone at the time. If there's one pile left with 5 stones in it, you can take all 5 because you can pick that pile and take as many as you like from that pile. So if there was one pile with 5 in it, and it's your turn, you win the game. All right, so let's do the same thing. Pause the video, find someone to play with, and see if you can figure out a strategy for the 3-4-5 game. All right, so you've played the game with someone, and if you play long enough, hopefully you will find all the P positions. You will find some more readily than others. There are a couple of P positions that people sometimes struggle to find. These are the ones that are closer to the beginning of the game rather than closer to the end of the game. But again, remember we're going to analyze these in between by playing backward, but also by recognizing certain things as we're playing forward. Now what we can do is completely brute force this and try every possible sequence of moves. Say, if I do this, then what happens, and this, and then back and forth, and try every possible move. In the 3-4-5 game, there aren't that many moves, and we could analyze that completely. But partially, we have this idea of playing the game enough times, looking at the data, see if we can recognize the positions. I'm not going to give this away yet. I want you to keep playing and make sure that you have figured out the P positions and if it's a player 1 game or if it's a player 2 game. Whichever player it is, you want to try to be able to describe the strategy for that player. What should they do in these different settings? In other words, if you can describe the P positions, then all you have to remember when you're playing the game is what positions do I want to get to. And as a person, we can recognize which of those positions we want to be able to get to and how do you get to it from a given state. If we were writing code for this, again, we have to be more careful. We have to be more precise so that every state we make the correct choice to progress and move forward. All right, so there's apparently an ancient game called NIM, and the 3-4-5 game is really an example of NIM, a very specific setting. So what happens is you begin with n piles of stones, and each of those piles has as many stones as you like. They can be a different number in each of the piles. It can be the same number in each of the piles, whatever you want. You just have some collection of piles of stones. Players alternate turns, and again, the same rules as the 3-4-5. You pick a pile and remove as many stones from that pile as you like. Again, the goal is still to pick up the last stone. And NIM is this, again, older game, but around 1901, a paper was published where someone analyzed NIM kind of in a formal approach for apparently the first time. And maybe that's when the name NIM was given. Again, there's some question about where the name came from. There is a German word that means to take that it could come from. There are some other things that it could come from. But whatever it is, the game is any number of pile of stones you like, and each of those piles can have as many stones in it as you like. But the goal, the way you play, is you still just go back and forth, picking a pile, taking some stones from it, back and forth, and then somebody picks up the last stone at the end. In the 1901 paper, the analysis turns out that binary numbers are at the heart of understanding the P positions and how to win this game. So we're going to do this analysis with the 3-4-5 game. And what you do is you write the number of stones in each pile in binary. So if we had the 3 pile, let's say it's pile A, has 3 stones in it. So 3 is written in binary as 1, 1. But because 4 and 5 need 3 bits, I'm going to go ahead and write this as 0, 1, 1. Pile B had 4 stones in it, so in binary that's 1, 0, 0. And pile C had 5 stones, so that's 1, 0, 1. And what we do to determine the P positions, it turns out that we calculate something called the nim sum. And the nim sum is add the column, but add the column in mod 2 calculations. So if there are an even number of ones in the column, the sum is 0, and if there are an odd number of ones in the column, then the sum is 1 for that column. So if we look at the leftmost column, it's 2 1s and a 0, so that total is 2, but mod 2 is 0. The next column, there's a single 1, so that's a 1. And the rightmost column has 2 1s, and so again, in the mod 2 calculation, that is 0. So this is a parity check. An even number of 1s records as 0, an odd number of 1s records as 1. If there are no 1s at all, 0 is an even number, and so that adds to 0 as well. All right, so the nim sum of this state, this board state, is 0, 1, 0. And it turns out that the P positions all have a nim sum of 0. So we have a board that does not have nim sum of 0. It does not have nim sum 0, means that is not a P position. That means it's an N position. That means the next player to move has the advantage. Well, since this was the start of the game, the next player to move is player 1. And player 1 needs to make this sum be 0. And how does player 1 make this sum be 0? Player 1 needs to change this middle column so that its value is 0. So they need to get rid of that 1 that is in that second column. But that 1 in the second column corresponds to the number 2. And so what is player 1's first move? Player 1's first move, let's get rid of that 1. Get rid of that 1 by removing 2 from the pile that had 3 in it. And so what happens then is you give this to the other player with a 1, 4, 5, and 1, 4, 5 nim sum is 0, 0, 0, and the other player will then have to break the 0 and give it back to you, or back to player 1, in a position that player 1 can then again make the nim sum go back to 0. And so in some games, this nim sum starts off at 0. If we put different values on here, the nim sum would start off at 0. That means player 2 has the advantage. But in other settings, player 1 has the advantage. And so whichever player has the advantage can maintain that all the way through the entire game. So let's look at an example with more piles. Let's say we have a pile of 7 and 11 and 9 and 14. And then we throw in a pile with 6. So we have 5 piles here, all different numbers of stones in each pile, and we need to calculate the nim sum. And we can look through here at the leftmost column. There's an odd number of ones, so the value there is 1. Odd number of ones in the second column, an even number in the third column, and the rightmost column an odd number again. So our nim sum is 1101, and we need to turn that into all zeros. So think about this. Pause the video again. Think about what you could do to get the sum to be all zeros. All right, so looking at this leftmost column, we have the 3 ones, and we need to get rid of one of those ones. We need an even number of ones in that leftmost column. So we need to get rid of one of them. We can't get rid of all 3 of them because we can only remove things from one pile. So let's just pick the top pile, pile B. And so we want to remove that 1, which corresponds to removing 8 from the pile. But we don't want to make that a final choice at this point. We're going to set the 8 over to the side momentarily because we may have to put some back to make other columns work out the way we want to. So we know we are working in the row here, the second row of items. So if I take away the 8 here, that gives the first column, the leftmost column sum a 0, but the second column is still going to be 1. So what I want to do is the 8 that I remove from here, I want to put 4 of them back, so that turns into a 1. So what I've done is I pretend that I'm taking away 8, but then I put 4 of them back. So these 2 columns, the leftmost columns, are both zeros. The third column is already 0. And then the rightmost column has 3 ones in it. We can only work with the second row, so I need to get rid of that one as well. So I need to remove 1 more. So the idea here is you start with column B, or pile B, stack B, take away 8, then put 4 back, and then remove 1. So what is the move that we've actually created? We've actually taken 5 away from pile B. If you take 5 away from pile B, that leaves 6. And if you calculate the nim sum, that nim sum is all zeros again. So this is one possible move that we could do. We could have modified pile B, possibly pile C, excuse me, or pile D. But modifying pile A or E won't help us because those two don't affect the leading one in the nim sum. So the only possible moves we could have would be to take something from B, C, or D. The thing we would want to do if it were B would be take away 5 from there. But we could analyze to see if there was a winning move from C or if there was one from D. And the analysis is the same in those situations. You take away 8, but then you might have to put something back, or maybe you take away more. And so the move from C or the move from D, you can analyze those and see if you can find a winning move that involves starting with pile C or pile D. Again, there are no winning moves that start with pile A or E in this particular starting scenario. All right, and of course, since this is a two-player combinatorial game, there's also the misere version. It's almost exactly like NIM. The difference is whoever picks up the last stone loses. And so on this one, again, I would like you to play the game, find all the P positions, see which player has the advantage. Remember, in the 3, 4, 5 version of NIM, player 1 has the advantage. With your partner, play the 3, 4, 5 version of NIM misere and see who has the advantage. Does it switch to player 2, or does player 1 still have the advantage? And once you know who has the advantage, see if you can determine what that winning strategy looks like. All right, so in keeping with our idea of modifying games bit by bit, there is a game called NIM K, where K is a number. It begins exactly like NIM. You have n piles of stones with how many ever stones in each pile. But the difference in NIM K is you're allowed to pick up to K piles and remove as many stones as you want from each of those piles. So if you were playing, say, NIM 2, instead of just picking stones from one pile, you can take as many stones as you like from 2 separate piles. You can remove the piles completely, or just take one from something, or just take one from one of them and not even touch the other one. You don't have to take from 2, but you're allowed to take from 2 if you like. And so in NIM K, it just adds this extra bit that says I'm able to take from up to K piles, and each of those piles I can take different amounts as long as I take at least one stone on my turn and don't take from more than K of the piles. Now, if K is greater than N, this game is really boring. If I'm playing NIM 7 and there are only 6 piles of stones, whoever goes first just takes all the stones and the game is over. So the game is boring if K is bigger than N, so we're going to only consider situations where K is less than N. Again, to analyze this, it turns out that this is exactly, the analysis is exactly like NIM, except we don't calculate the NIM sum in terms of an even or odd number of ones. We calculate the sum mod K plus 1. So if you think about what really happened, in regular NIM, that's really NIM 1, and we do our calculations mod 2. If we were playing NIM 2, we would do our calculations mod 3. So you want 0 ones in the column, or 3 ones in the column, or 6 ones, or 9 ones in every one of the columns, and so on. That continues on. So the analysis of NIM came out in 1901. NIM K was introduced and analyzed, I think, in 1910. And so let's look at the K equal 2 situation of the 3, 4, 5 game. All right, so we're doing our calculations mod 3 now. And in the mod 3 world, remember the values are 0, 1, 2, and then it wraps back around. So 0, 1, 2. And so if we look at these columns, the leftmost column adds up to be 2, the middle column adds to be 1, and the rightmost column adds to be 2. And so our NIM sum is 2, 1, 2, and we want to turn that into all zeros. Remember that the only way to get sums of 0 when there are only 3 piles is to have no ones or 3 ones. So no ones or 3 ones in every one of the columns. So this means that we are going to have to look at these two values. These 2 ones are going to have to go. We can't have those values in here. So that's going to have to go away. So we're going to need to remove temporarily 4 from each of these 2 piles, but then we need to make the other pieces work correctly. Since we can't affect the 1 in pile A now, because pile A is off limits to us, we're only allowed to touch piles B and C, we need to put a 1 back in the second column here, and then we will need to put a 1 back in the third column, the rightmost column for B. So what did we do? We took away 4, but then we put back 2 and put back 1. So what we really did in column or in pile B was we removed 1. We started with 4 and we put it as 3 in the pile. For the 5, we take away the 4, so that puts a 0 in the leftmost, but we need a 1 in the middle, so that means we have to put 2 of them back. And then we don't bother the 1's place, so what did we really do? Take away 4 and put 2 back. What did we really do? We took away 2 from that pile. So a first move is take 1 from pile B and take 2 from pile C, and that leaves us with a nim sum of 0, which means we have now given it to the other player in a position that they cannot win. They're going to break the balance, and when we get it back, we can restore the balance, and they're going to break the balance, and we can restore it, and so on until we get it down to the nim sum of 0 by picking up the very last stone wherever it happens to be. It might be stones in 2 separate piles, and we can then take all the stones from both piles. Whatever happens, we have control now. We have turned a position that was an N position into a P position, and we have control of the game. If you made K equals 3 in this game, then it's again boring because the first player just takes all the stones and the game is over. So we would only have to analyze the 3, 4, 5 game as K equals 1 or K equals 2, and then of course the misere version of each of the games. All right, let's switch to a different game. This one is called 15 Finesse. It is credited to a famous problem writer named Martin Gardner. And so what happens in 15 Finesse, again, this is a 2-player game, and we have cards just numbered 1 through 9. You could use a regular deck of cards and just take out ace through 9. And they're just laid face up on the table between the 2 players. And the players take turns, take 1 card at a time, and put it on your side of the table face up. Just lay it down face up so everyone can see what you have and no one will forget what you had. The other player takes 1 card, you take a card, they take a card, back and forth, back and forth, back and forth. And you do this until one of the players can use 3 of their cards to make the total 15. So it doesn't matter how many cards you have. You might have 4 cards, you might have 5 cards before you can do it. It's possible, but as soon as 3 of your cards add up to be 15, then you have won the game. All right, so exactly 3, total 15, you win. So play this game pause the video, play with a partner, see if you can figure out a winning strategy for 15 Finesse. But more importantly, see if you can figure out what this game really is. You've played this game before, you just didn't play it with cards. So pause the video, play for a while, and come on back. All right, so maybe you recognize the game, maybe you didn't. The game that it really turns out to be that you were just playing is Tic-Tac-Toe. Now, we're going to analyze a different game called Extreme Tic-Tac-Toe, but Tic-Tac-Toe you've played has the board like this. It turns out that those values 1 through 9 correspond to putting the numbers 1 through 9 on this grid in certain ways so that every column and every row and all the main diagonals add up to be 15. So there is a way to do that. It's something called a magic square. There's more than one way to put 1 through 9 on there, but you can put 1 through 9 on there to correspond to 15, and then what you do is select the cards that will correspond to how you would play tic-tac-toe. And so again, we know playing tic-tac-toe that 15 Finesse is really not a combinatorial game because you can tie, and once both players realize that 15 Finesse is really just tic-tac-toe, they're going to always make the play that will block the play that you were trying to do, and so on. But if you don't see the geometry of that addition game, then 15 Finesse seems like a completely different game, and it seems much more complicated than tic-tac-toe. Now, the first time you played tic-tac-toe, you almost certainly lost, and probably the second time and the third time and several times you lost, but then you started figuring out how to tie the game. And the only way you can win tic-tac-toe is to either play someone who's never played before or play someone who hasn't played for a very, very long time and has forgotten how to play. The only way to win at tic-tac-toe is for the other player to make a mistake. It doesn't matter whether you're player 1 or player 2. Player 1 is trying for a win, and player 2 can always block them. If player 2 tries for a win, player 1 can always block. So we're going to look at a more interesting version of tic-tac-toe. This is called Extreme Tic-Tac-Toe. And so how do we make tic-tac-toe extreme? Well, there are versions that I've seen before where people go with a 3-dimensional board or do some other kinds of things, but we're not going to do that. We're going to put some smaller boards in the middle. But then we're not going to quite play it the way that you're thinking. We still want to win by winning 3 boards in a row in some direction. But let's say player 1 played an X here on their first move. They just decided to play in this portion of the grid. We don't have to play this grid all the way out and then move to the next one, move to the next one, and so on, because what would happen there? You're going to tie in every grid that you play. Well, it turns out to make this game more interesting as a 2-player game that player 1 played their X in the middle right-hand portion of the board, which means that player O has to play on the middle right-hand subgrid in the main portion of the board. So where player 1 played tells player 2 which part of the big board they have to play in. It doesn't tell them where in there they have to play. They get to choose that, but they have to play in this portion of the board. So if player 2 then puts an O down here in the bottom middle, this would mean that player 1 has to play down in the bottom middle. And so you get this more exciting version of tic-tac-toe where the other player's move tells half of what your move has to be, or part of what your move has to be. Now, as you continue on in this game, if you keep playing, you see things like eventually one of the small boards gets filled up. or someone wins that board. So if, say, let's say X were to win this small portion of the board up here, the rules on this vary. The version that I like to play is that if X has won this part, then X can still send O there by playing an upper left-hand corner somewhere. But if O plays an upper left-hand corner and X has already won this, then X can play anywhere on the board that they like. They can play any grid, anywhere they want, as long as there's an open position there. The other portion is if the board, the small subboard, is completely full, and if a different player says you have to play there, it doesn't matter whether you won that one or not, you can play wherever you like. The other thing is, once one of the small boards is won, then the other player can't take that away. So if player X had X is all the way down here and then O filled up the rest of the board, O doesn't get to take that away from X. X already won it. So Extreme Tic-Tac-Toe is a lot of fun. It's not like regular Tic-Tac-Toe, where you know immediately that you are going to tie. It is possible to tie in this game, and it is also much longer play, though. When people play tic-tac-toe regularly, it just takes a couple minutes. Extreme tic-tac-toe, maybe just a few seconds on regular tic-tac-toe. Extreme tic-tac-toe can take a very long time. And the main thing is you don't know what's happening when you first play it the first few times. You're just making moves at the beginning, and it's only as you get into the game that you start analyzing the situations and thinking about what you really want to force to have happen. But as far as the analysis goes, there are better moves than other moves, even if you don't know what they are yet. And so Extreme Tic-Tac-Toe is a lot of fun and usually goes over pretty well with a wide variety of age groups after they get bored with regular tic-tac-toe and want something to fill some time when they don't have their phone ready or they're not allowed to have screen time and so on. The Extreme Tic-Tac-Toe is just a fun way to play a grown-up version of regular tic-tac-toe. So another similar game that's similar in the sense of a player partially telling the other player what needs to happen. This game is kind of like Connect 4, except gravity's not involved. And so the board starts off with a 6x6 grid, and they're labeled A through F and 1 through 6. The game was created by a couple of authors, one of whose surname was Foresight, and so they created the game Foresight as a play on his name. But in this game, what happens is on your turn, you pick a row or a column, and then the other player finishes your move for you. So let's say it's your move and you pick column A, then right now the other player can pick whichever row they want by picking 1 through 6. And the goal is to get 4 in a row. So again, you're placing your X or O or whatever thing that you have, whatever way you're playing the game, whatever you're placing on the grid, but you only get to pick half of your move. You pick a row or you pick a column. They pick the rest of it. You put the piece down. Then it's their turn. They pick a row or a column. You pick the rest of it, put it down. You don't have to pick a row every time. You don't have to pick a column every time. Whatever choice, you just have to pick one of the two and they pick the other half of your move. So again, it's kind of like Connect 4, only you don't get complete control over your entire move. You only control half of your move, and then you control half of their move. And as soon as someone gets 4 in a row, the game is over. All right. Another game, I think is the last one we'll talk about, a game called Mediocrity that was created by a man named Douglas Hofstadter. Mediocrity is, at least the version we're going to discuss, is a little different than his version. We're going to discuss it as a card game, but not as a card game with chance involved. It's just cards to keep track of what you've already played and what you have left that you're allowed to play. So in the standard play of Mediocrity, it's a 3-player game, so that's a variation of the other theme. But everyone just has 5 cards numbered 1 through 5. There's nothing special about the cards other than just keeping track of what you have already played. So you have these numbers 1 through 5, and all together, everyone is going to select a card and play it, just throw it face down in the middle of the table, all at the same time. And the player with the middle value wins the point. So, for example, if you all played and the 3 cards in the middle were 3, 4, 5, then whoever played the 4 gets the point. They take the cards off the table and they scored a point for that. And then we play another card. If you played the 3 already, you don't have a 3 left, it's gone. You play something that's left, and you keep doing this until all 5 cards are played, and so 5 points get awarded. Now, if you thought about this for a second, you probably thought, wait a minute, what if 2 people play the same card, or everybody plays the same number? Who's in the middle then? Well, it turns out that we have a tiebreaker. Before we actually start playing the game, we're going to select a color. Everyone just picks a color, red, green, or blue. One player is red, one is green, and one is blue. And the way the tiebreaker works is that red is always bigger than green, and green is always bigger than blue if there's a tie. Now this isn't rock, paper, scissors. It doesn't wrap back around that blue is bigger than red or anything like that. Red is bigger, green next, blue is smallest. And you might think, well, that's a disadvantage for one player or the other, but let's take a look at a couple of situations. Let's say that red played the 5 and green and blue both played 4s. Which card is in the middle now? Well, 5 is bigger because 5 is bigger. But then the green 4 is bigger than the blue 4, which means that the green 5 is in the middle, so green wins the point. But what if green and blue still both played the 4, but red played a 3? Now in this situation, the green 4 is still bigger than the blue 4, but the 3 is smaller because 3 is smaller. The color doesn't matter at that point. And so now what happens? In that case, blue won. And so there are situations here you can see that it's not just, oh, well, green's bigger than blue, so green's going to win. In this case, because green was bigger than blue, green lost. Green had the biggest card in that situation. All right, so what you do is we keep track of who played which card. So I have made some sets of cards that have red 1 through 5 and green 1 through 5 and blue 1 through 5. So you know who played which card. And we can always tell which card is in the middle and who has won. All right, so if you think about playing the game, who wins the game then at the end? By the way, sometimes people play this with 1 through 10 instead of 1 through 5. Just 1 through 10 takes longer to play, but you can do that. Again, the same thing in the standard play for the game. You have 3 players. Each player has their 5 cards of their assigned color. Everyone selects a card and plays it. The player with the middle value wins the point. You go until all 5 cards are played, and then who wins the game overall? Well, why change the rules now? The player with the middle number of points is the player who wins the game. All right, so what happens if somebody wins all 5 of them? Let's say player red wins all 5. Then green and blue got 0, but green's 0 is bigger than blue's 0, so green wins the game. What if it were one player wins 3, one wins 2, and one doesn't win any at all? Well, the player who won 2 wins the game because 2 is in the middle. But this is just for the one hand. The way you play the whole game is you play the whole hand, all 5 cards. Now one of the players won that, right? They had the middle number of points and they win the game, or they win the hand. Then you play again, and a player wins the hand. And you play again, and a player wins that hand. So there are 5 hands in all. Who won the middle number of hands is the player who wins the overall game. All right, so mediocrity is this goal of being in the middle, but not being in the middle too many times. Right? You want to be in the middle the correct number of times to be able to win the game. If you're in the middle too much, you're too mediocre. If you're not in the middle enough, you're either too good or too bad. So what is mediocrity about? It's being really mediocre at being mediocre. So, as usual, feel free to ask questions in the comments, by email, or on Discord. I hope you have a lot of fun playing some of these games. And as usual, have a great day.